All right, so we mentioned in the last class that there's going to be a couple number systems we deal with. We mentioned base 10. We deal with base 10 numbers, well, because humans deal with base 10. We deal with base 2 numbers because computers deal with base 2. Anything you store in a digital device is stored in binary, and the binary number system is a base 2 number system. The other two number systems which I'll introduce you to today, one is called octal and the other is called hexadecimal. Neither the computer or humans deal with that directly. It's just a convenient way to represent a bunch of binary bits. So rather than remembering a bunch of zeros and ones, if you learn how to work with octal or you learn how to work with hex, you'll see that the string of binary digits is a lot easier to work with. And typically that's used for addressing. And I'll show you examples of that. So getting into the PowerPoint, the reason we want to know about number systems is because basically, as we discussed in previous classes, computers are devices that store numbers. All they can do is store numbers. So no matter what you do, whether it's a picture, a video, a Word document, it doesn't matter, it's stored as a number, binary number. And so we talked about general number systems. I used the base 10 number system as an example, but any number system follows this schema. Any number system, you'll have the base, and the base gives you some information about the number system. And then the power. Power gives you information about how to use that number system for position weighting that we discussed in the last video. So now here the base, or the radix, tells you how many symbols you have in a particular number system. And if you take the base minus 1, it'll tell you the value of the highest digit in the number system. So a base 10 number system, this is what humans use. Base 10. This base says that we're going to have 10 symbols. If you take 10 minus 1, you get 9. So 9 would be the value of the highest symbol. Now this will work for any number system, not just base 10. So, most people, most humans, most people are familiar with base 10. But the base 2 number system, we'll talk about base 8 number system, we'll talk about base 16. You can even make up your own number system, which I might ask you to do on the exam, and it will follow the same schema. So I'll show you an example of what I mean by making up your own number system. So just kind of review. We talked about the base 10 number system and that the fact that what you call place value, the ones place, the tens place, the hundreds place, if you write it kind of as a power of 10, then this ones place, that 10 to the 0 is 1, and that 10 to the first is 10, 10 to the second is 100. What this does for us is then the exponent becomes the position of the digit that goes in that box. And that's kind of convenient because we said that computers always start counting with zeros. So you want to remember when we count as humans, we start with 1, computers start with 0. And so this lends itself very well for what we want to do with digital devices. The fact that that exponent is a 0, we can use that as the 0th position. And that's the way to think of it. And so the binary system works the same way. It's a base 2 system, which means that we're going to have 2 symbols. If I take the base minus 1, 2 minus 1 is 1, so the value of the highest symbol will be a 1, and the 2 symbols that we're going to use would be 0 and 1. So we looked at that. Now, we know and understand that it's pretty easy to represent a 1 or a 0 with the voltage. Either with a static 5 volts or 0 volts, I can represent a binary 1 with 5 volts, binary 0 with 0 volts, and I can actually move those 1s and 0s around by making something called a waveform, this is an example of a waveform. So it's easy to represent a 1 or a 0 in binary using what we call two-state electronics, the presence or absence of a voltage. So that makes the binary number system another reason why we want to use a binary number system is because of the easy representation of numbers using voltages. Here's some definitions for you. Some of these we talked about before, so I would say mark this slide if you're keeping track of things to kind of be aware of for exam or quiz material. You kind of already know that each binary digit is called a bit. You may or may not know that in a PLC, now when I say PLC, computer, any digital device, but specifically speaking to the PLC, in the PLC, the processor contains many thousands of locations called registers. And then the next point, it says registers are also called words. And that really is, strictly speaking, is not true. Strictly speaking, a register is a piece of hardware. You can actually go to the electronics store and you can buy a register, a shift register, or some type of register, and it would be the purpose of that register to store binary data or information. So a register is an actual device, a piece of hardware. A word is a virtual construct. It doesn't exist. It only exists in memory. But for the purposes of this course and for the purposes of PLCs in general, you can consider a word and a register to be the same thing. So this is what we're going to use to hold those bits that map or tie directly to the input-output modules of a PLC. Each cell, if you can think of a register, is just a row in an Excel spreadsheet. If you have a 16-bit register, you have 16 cells, and each cell can hold a 0 or 1, and each cell position is mapped to a physical screw terminal on the input or output module of the PLC, and depending on whether that switch is open or closed, there'll be either a 1 or 0 in that box. And that's the reason why knowing the word size for a PLC is important. If you have a 16 connection point PLC, then the word size is going to be 16 bits because you have to keep track of 16 switches or buttons, whether they're open or closed or not. So kind of a counting thing. And I'll show you an example of that. Actually, I already showed you that input-output image table, but we'll revisit that before the class is over, and I'll connect a couple points, hopefully. We mentioned the fact that I think in the other class that the word size is, whereas we know a bit is a single binary digit, a byte is 8 bits. A word size depends on the manufacturer of the PLC. They can make any word size they want. There's common word sizes, but I think 8 bits, 4 bits, 16 bits, 32, but they can actually be any size. Let's see here. So I think, yeah, it says 16 bits are most common. So I think that's all I want to do here. This slide here, we talked about in the last class, we talked about the LSB, the least significant bit, and the most significant bit. You want to be familiar with those. This is important to keep track of when you're sending data back and forth. Sometimes they send the LSB first. Sometimes they send the MSB first if they're doing serial data transfer. So it's you kind of want to be able to label and talk about these bits. The other thing to note, and we didn't talk about this in the last class, is that in this class a word, and a word's going to be 16 bits, and remember 8 bits is a byte, so there's actually 2 bytes in the word for us in this class. And so not only can we talk about the least significant bit and the most significant bit, we can also talk about the lower byte and the upper byte. So you can kind of use this to identify positions in the actual word. So these are some terms to be familiar with. MSB, most significant bit, LSB, least significant bit, and the upper and the lower byte of a 16-bit word. And knowing that we're going to use 16 bits for a word, you want to mark this slide and be able to do a simple calculation like this. So given the word size, if you know the word size, you should be able to tell how many individual pieces of information a particular PLC can store. How many zeros and ones can it physically keep track of? And so make sure you follow this. If the memory size is 884 words, and one word is 16 bits, if you take the product of the 884 and the 16 bits, you can actually mapped to this many individual zeros and ones. So that many individual pieces of data can be stored. Now remember what I said a couple days ago, one very important difference between a PLC and pretty much every other digital device on the planet, more or less, is that the PLC can actually address an individual bit. It can address a single bit, whereas most digital devices address bytes. So your PC, your cell phone, your microwave, it can only address bytes, 8 bits. So this makes the PLC kind of uniquely special. And since each bit position can represent a switch or button or some type of device, well, for this particular calculation, that's how many switches or buttons you can connect to it in theory. If we change the scenario a little bit, still have 884 words, but a word is 8 bits. Same calculation. This time we can only store about 7,072 individual pieces of information. So mark this slide, know how to, given the word size and memory size, you should be able to calculate the number of individual connection points. So mark this slide. And typically, you don't really need a whole lot of memory, not like in general, I'll say you don't need as much memory for industrial processes as you might need just for your personal PC. So normally PLCs have a small amount of memory. You know, the smaller PLCs, maybe 1 or 2 kilobyte. Remember, a kilo for us is not 1,000. If you see a capital B after the K, then a kilo is 1,024, 1024. All right, so we did some of this already in class. If you want to do some converting binary to decimal, I call this 8421 code. So just make a grid, a box like this, and then put your numbers in there, 8421. So put these numbers in this box, and then you can just put your bits over top of that, and you can figure out how many, what the decimal equivalent of a particular binary number. So remember, if you type a decimal number and you put that into a digital device, when you hit enter or you hit submit or whatever it is you hit, and it goes into the microprocessor of that device as zeros and ones. So here, if you think about what you call place value, or what in digital electronics they call the weight, this has a place value or weight of 1, 2, 4. So this is saying that you take the weight and you multiply by whatever the digit is in the box. So 1 times 4 gives me a 4. 1 times 2 gives me a 2. So if I type 6 on my cell phone screen and hit enter, then what actually goes into the microprocessor in your cell phone is this right here. What actually gets stored is 0, 1, 1, 0. And remember, this is machine language, but on the lower level, the actual presence or absence of a voltage is what these zeros and ones represent. So you can drill all the way down to see what's happening under the hood. But pretty much we stick with the binary. We don't worry about what's going on in the machine as far as voltages and currents. So I would say you should know how to go from binary to decimal and then the reverse. Pretty simple. You just kind of do the reverse if you want to convert decimal to binary. I need a 12. And what I mentioned in the last class was if you make your 8421 code, 8421, and remember as you go this way, binary doubles. So this will be 16, which is bigger than 12. So I know to stop at 8. I can stop at 8, and then I say, all right, I can take an 8 out of 12. I know I got at least 1 8 in that 12, and I still got some left over. Matter of fact, if I take 12 and subtract 8 from it, I get 4. So I know I got at least 1 4 in that 12. And these two together is going to give me 12, so I'm just going to put 2 zeros on there. So a 12 base 10 inside your PLC or your cell phone or your whatever, this is what's stored inside that device, if it's a number. And we'll talk about you know, remember everything is stored as binary. So if we're talking specifically numbers, it's going to use this position weighting that I'm showing you right now. If it's a letter or a character or something else, it's going to be stored a different way, and I'll show you that here if we don't run out of time. I showed you this example in class where you can use what they call repeated division. So you can actually, if you have a really, really big binary number, you can use this method of repeated division, where you just take the number, the decimal number, and you keep dividing by 2. And whatever the remainder is, that becomes the binary number. You just got to remember that the first one you get is your LSB. It's not your MSB, it's your LSB. So as long as you remember that, then the divide by 2 method is pretty simple. I like, personally, when I do this stuff, I like to I just do it this way. You know, unless I want to show how smart I am, I might do the power divide by 2. But the position weighting works pretty easy. It's pretty easy. So we went through all of that in the last class, and we got to this thing about, well, what if I want to represent a negative number? How would I represent a negative number in a digital device, since we know that the only thing that can go in the register cell is a 1 or a 0? You can't put a plus sign in the register, and you can't put a minus sign in the register. It's not possible to represent these symbols in a register. So how would you represent a negative number? It turns out there's 3 ways, and we kind of went through this rather quickly, but there's 3 ways, and we talked about 2 of the ways. We talked about the 1's complement and the 2's complement, which probably won't make sense until our next class, how these represent negative numbers, at least the 2's complement. But you want to know how to take the 1's complement, and you want to know how to take the 2's complement. So there's 3 ways to represent binary numbers. The most common of the 3 ways, I would say probably the 2's complement is most common, and then second to that is the sign bit, use of a sign bit. I don't think the 1's complement is used that often. Sometimes they use the 1's complement to get to the 2's complement. So you want to know how to take the 1's complement and the 2's complement. Since I didn't do I'm not doing an objective sheet for each module I present. I'm just going through telling you which slide to remember. So you want to remember 1's complement, 2's complement. Let's look at sign bits. Here's how that works. So if your computer uses a sign bit, or your device uses a sign bit, then what happens is the actual that position weighting. So like this place right here, this place right here, this place right there. You would actually have place value for these places, but then the leftmost bit, that's your sign bit. So this does not have position weighting. A 0 in this first position, if you're using the sign bit, going to represent a positive number. And a 1 in that first position is going to represent a negative number. So like right here, if you look at this, this is the magnitude. This is where you apply that 8421 code. So if you think about it, this first place right here, that's a 1. So I got a 1 there. And this place right here is a 4. So I got a 4, I got a 1, so I know that's a 5. I know that's a 5, but to get the plus 5, the fact that there's a 0, that leading number is a 0, then I know that this is a positive 5. Down here, look at this one. Same thing, I got a binary 5 right here. But since my sign bit is a 1, I know that will be interpreted as a negative 5. So one way to represent a negative number in a digital device is to use a sign bit. Now, it's important that you know that if you walk into a room and you look at a whiteboard and there's a digital number on it, you have to be told that we're using a sign bit. Else you don't know. You don't know if we're using the sign bit, then my most significant bit is going to be right here. If we're using the sign bit, this is my most significant bit, because that's my magnitude. If I'm not using the sign bit, then my most significant bit is going to be right here. So given an arbitrary binary number, I have to tell you, or you have to be told, hey, this device uses a sign bit, and then you would know that the not the leftmost, but the next one to that would be that would start your magnitude, and that would be your most significant bit. The other way to represent a negative number is the ones complement. That's really, really easy. People like the ones complement because there's devices. We haven't really talked about gates in here a lot, but we will. Basically, a logic gate does with those switches. Remember we talked about and logic, or logic, not logic. We talked about those circuits. Well, we actually, electronics have gates that mimic those circuits. So a gate is a circuit that, there's an AND gate. It mimics switches in series. There's an OR gate. It mimics switches in parallel. There's a NOT gate. And if you remember the truth table for NOT, it basically changed the state of a bit. It changes the state of a bit. So the ones complement is easy to do because we can just simply use a gate called an inverter. Because what an inverter will do is just flip bits. So when you take the ones complement of a number, all you do is flip the bits. So any place you have a 1, you change it to a 0. Any place you have a 0, you change it to a 1. So this number right here is the ones complement of the one on the left. And then the one that's really important though is this one. This is the twos complement. Now there's two ways to do the twos complement. It might be more, but two main ways to do it is, one way is to take the ones complement and add 1. You can do that. You gotta know how to do binary addition, which it's not that big of a deal. I like to do it the way I'm showing you on this slide though. I like to say, all right, if I want to take the twos complement of this, up to and including the first 1, up to and including the first 1, you leave all those bits the same. So I won't mess with these. After the first 1, you take the ones complement of what's left. So I left these the same. And then I took my original number and I took the ones complement of it. This is the ones complement of it. And I just put those two together and I have the twos complement. So if you do it that way, in my opinion, it's a lot easier to me than taking the ones complement and adding 1 to it. Okay, so you definitely want to know how to do the twos complement. Matter of fact, when we'll do some binary arithmetic. And the way we're going to do it, we're not going to use the ones complement. We're going to use the twos complement when we do the arithmetic. So you want to know how to do that. Okay, so I think that's it for this particular part of our discussion. So that was the binary number system. Anybody have any general questions on the binary number system? Or I can ask you to make up your own. On the exam, I can say, make up a number system, or I can give you a number system that's weird, like a base 4 number system. So if I say, all right, you got a base 4 number system, so I got 4 to the end, that means I'm going to have 4 symbols, and the symbols, I take the base minus 1, so the highest value that I can have in a base 4 number system would be that. So then I can go my position weighting. This will be, it's always the base of the 0 power. This is 4 to the 0. That's the weight or place value of this position. This is 4 to the first. This is 4 to the second. So this will be a 1, a 4, a 16. And I can put the digits 1, 2, 3. I can't have a 4. Excuse me, I can't have a 4. Because the highest digit I can have in the base 4 number system would be a 3. So I can make up my own number system, and I can actually convert that. If I have a 1, 2, 3, this would be, now we're dealing with number systems, so I have to say what base I'm in. And the way I do that, this would be a 1, 2, 3, base 4 number system. I can convert that to base 10 by just saying I got 1 times 16. So we got a 16. I got 2 times 4. So it'll be plus 2 times 4. I got 3 times 1. So this will be a plus of 3. I add that up and I get my equivalent in base 10. So something like this you should be able to do. Only as, hold on a second, guys. I'm still dealing with that light thing. But this is only as an exercise. This has no practical application to PLCs or digital devices. But other than to open up your mind and see that I can have any, we are familiar with base 10 number systems because that's what we use, but you can have any number system. If God had given us, instead of 10 fingers and 10 toes, if God had given us 7 fingers and 7 toes, we'd have a base 7 number system. So it's arbitrary, but interesting. Okay, let me go to the next 2 number systems I want to talk about. We mentioned there were other number systems. Well, the 2 main ones used with digital devices outside of binary is octal and hexadecimal. Now remember, the computer only understands binary. It does not understand base 10. It does not understand octal. It does not understand hexadecimal. They call hexadecimal hex for short. So anytime we use those numbers, if I want a binary, if I want a decimal number to go into a digital device, it's going to be changed to binary. The same can be said of octal and hex. If I want a hex number to go into a digital device, then I gotta have a conversion process that converts it to zeros and ones, and we'll see how to do that. So why octal? Why hex? Why use these? Well, if I express everything as binary, you'll see that if I represent all those zeros and ones in other bases higher than the base 2, it takes fewer digits to do it. So that's the reason for this. It's much easier to remember the octal number or a hex number than it is a series of ones or zeros. So we deal with the octal number system first, in base 8. Well, let me go away from here. Let me come back to the camera because I want to show you something. If we were in our number system, base 10, it means we have 10 symbols. If I take 10 minus 1, I get a 9. So the value of the highest symbol in the base 10 number system would be 9. So my actual digits, though, are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I want to count, I do like this. I say, all right, I got 0, I got 1, I got 2, 3, 4, 5, 6, 7, 8, 9. Uh-oh, I'm out of digits. What do I do when I'm out of digits? When I'm out of digits, then what I'll do is I'll put the next digit here, a 1, and then I'll start to repeat these. I'll repeat these. I'll go 1, 0, 1, 1, 1, 2, 1, 3, all the way over up to 1, 9. And when I'm out of that, when I'm out of digits here, then I'll change this one to a 2. And all I do is repeat the 0 through 9 characters or digits. That's all I do. In any number system, it's the same way. So you'll see that here. I'll show you that here in just a second. So looking at the base 8, so the octal number system is base 8. Very, 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 very common in PLCs, especially older. Allen Bradley used octal for addressing. It's a natural because you know that there's 8 bits in the byte. So there's a natural connection between the number 8. So octal is a natural fit. And if we use our method of determining the number of symbols and the value of the highest symbols, it's a base 8, so we're going to have 8 symbols. 8 minus 1 is 7. So the highest digit we can use in the base 8 number system is a 7. We can't use an 8, it's a 7. We stop at 7. When I run out of digits, I got to start repeating, just like I showed you on the board a second ago. So this is important because students will make a mistake here. They say base 8. Well, that means you cannot use the 8. You don't actually use the 8. 8 and 9 are not allowed in octal. So look at this right here. In binary, it takes me to represent these numbers, 0 through 7. In binary, it takes 3 bits. The highest number here, 7, will be in binary, be a 1, 1, 1, right? 4, 2, 1. That's 7. Well, look, it took 3 bits in binary and only 1 digit in Octal. And this is the reason why we do this, why we use Octal and Hex. Excuse me, because I can use fewer symbols to represent the same information. I just got to be able to convert it back to binary if I need to. Our position weighting, just like base 2 and just like base 10, it's the same, nothing's different. We just take our base to the 0 power, and that gives us our place value or our weight of that position 0, position 1, position 2. So instead of the 1s, the 10s, and the 100s, or in binary, the 1, the 2, and the 4, in the base 8 number system, this is our place value or our weight. So I have 4, 6, 2. Now that little 8 right there, that's that subscript. That means that this number right here is an octal number. It's not 462 base 10, it's 462 base 8. If you want to convert it to base 10, then you got to do this math. You got to say, all right, I got 4 of these, so I got 4 times 64. I got 6 8s, so I got 6 times 8. And I got 2 1s, so I got 2 times 1. And you add all those up, then this is what you get right here. So our 462 in base 8 is a 306 in base 10. That's the way we would think about it as humans. Now, what's more important than that, though, is being able to go from octal to binary. And it's really, really, really simple. If you know the 8421 code, this is really, really, really simple. Because all you got to do is take each individual octal number and write it in binary. So but you only use 3 bits. It's important. You only use 3 bits. So here, if I want to write a 4 in binary, it's a 1 0 0 base 2. If I want to write a 6 in binary, remember this is a 4 in my 421 code. This is a 2. That's a 1. That's the place value in binary. So I got a 4, no, that's a 6. And then over here, that's a 2. So I put all those together, and this is what I get. It's much easier, though, to remember 462 base 8 than to try to remember all these zeros and ones. So this is the reason why we represent, even though we know it goes into the machine in binary, this is why we represent these binary numbers and other number systems. It's just easier to remember, easier to work with. But we can keep going with this. Once you learn how to do one number system, we can do any number system. And so another natural is the base 16. Well, why base 16? Well, base 16, you already know. For us in here, we said a word is going to be 16 bits or 2 bytes. So word size is, a common word size is 16 bits. So hexadecimal, the base 16 number system is another natural fit. So here's a comparison of binary, decimal, and hexadecimal. Now notice something that right here, I draw a line right here. I want you to compare decimal and hex. They're exactly the same. Exactly the same. So in hexadecimal, binary and hex are the same for the digits 0 through 9. Once you get above 9 in the decimal number system, then we start to repeat. I showed you that. We start to repeat this column right here. But over here, we don't do that. What we do is we use letters of the alphabet. So what you got to remember, and you want to remember this, you want to remember that, let me erase this. What you want to remember is that this A is 10, and for the next 6 of these, we just use letters of the alphabet. So A is a 10, B is 11, C is 12, all the way through F, which is 15. So all really hex does is it takes the binary number system and replaces the numbers 10 through 15 with letters of the alphabet A through F. So it would look something like this. Your position weighting says that this is 16 to the first, 16 to the second. Sorry, see, I didn't start with 0. 16 to the 0, 16 to the first, 16 to the second. So here my place values are our weights in the base 16 system. And here's the number. Now remember this number. This is 1B7 base 16. So when you see an alpha letter in a number, that means it's a hex number. If I want to convert this to decimal, do it the same old way. It's real easy. Just take this and multiply by your place value. So I got one of these. That's 256. I got B of these. What do you mean you got B of these? Well, before we said B, that's equivalent to 11. B is 11. So I'm going to multiply 11 times 16, and I get this. And then I'm going to multiply 7 times 1, add them up, and I see a 1B7 in base 16. And our number system would be a 439. So you want to know how to do that. Now, more important than that, though, is how would I go from hex to decimal? Because that's what you're going to want to understand more often. How do you go to hexadecimal? Well, that's really, really easy. And if it was octal, remember we wrote each octal digit using 3-bit binary bits. Well, all you're doing in hex is write each hex digit using 4 bits. So here I write a 1. And notice, even though I could have left off these leading zeros, I always show 4 bits. B, remember B that's 11. So this is 8, that's 4, that's 2, and that's 1. So I got 8, and 2 is 10, and 1 is 11. So there you go. And then 7. But then all these bits are high for 7. But notice each one of these I write with 4 bits. So it's really, 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 really simple. You just write each individual digit using 4 binary bits and put them together like this. And you'll see the conversion. But it's much easier to remember 1B7 base 16 than try to remember this. That's ridiculous. So now you can see why we would want to put numbers in other number systems other than binary. It's just easier to deal with. Now I want to go back to something since we studied this. But before we do this, anybody have any question on binary, octal, or hex? Any questions? Okay, let me go back to something. I want to go back to, where is it? Did I not upload it? Oh, here we go. Okay, look at this. Remember this? Now this actually turns out to be pretty important. In theory, they call, there's a virtual construct called a output image table or input image table. You pick up somebody's book, they're going to call the output image table or input image table. If you work with PLCs, in the real world, they're probably going to call it a data table. This is a data table. And the way to think of this is, I mentioned to you before, just think of this as a grid. These numbers right here, let me switch back to the camera. So just think of that as like a grid. So you got these rows, and those numbers represent cells. And it's 0, 1, 2, 3, 4, 5, 6, 7. And over here, you got these repeated. And these are like registers that can hold a 1 or a 0. But I want you to look at the way they're numbered. So now we go back and look at that. Look at the way these are numbered, guys. Look at this. Because before when I showed you this, I told you don't pay attention to the numbering. But if you zoom in on this, all this is showing is that this is 0, and you get over this side through 7, and then it starts to repeat, a 1. Right, so this is the octal numbering system. So these are really a bunch of registers, those cells that can hold zeros and ones, but each cell, instead of being numbered in decimal, they're numbered in octal. Right, they could have numbered them in hex. If you come down here at the bottom and read the fine print right here, it says that right here, if you read that, it says that Allen Bradley PLCs, some of them, they'll use the octal numbering system. So if these numbers didn't make sense before, and looking at these numbers, they should make a little bit more sense now. Now, the simulation software that you'll use, there's actually there's this data tables, several data tables in there, but you actually can convert them. You can convert the cell numbers or the bit positions to binary. You can convert it to all the number systems we talked about, and I'll show you that. You'll see that you can do that. So it's kind of handy. How much time do I have? I got time. Okay. Now, so if you remember, when we first started this conversation a couple days ago, you know that the only thing you can put into a digital device is zeros or ones. That's it. Zeros or ones. But there's two ways to interpret those zeros or ones. You can either have a number, in which case it's going to use the position weighting we just got through going through for base 2. Or you can have a code. What's the difference between a number and a code? Well, in general, a number is going to have position weighting, what you call place value. A code, more often than not, it's going to use the different bit positions to represent one piece of to distinguish one piece of digital information from another. It can also, though, use some kind of weighting system. So I think I got enough time to go through this one real quick. But I want to show you something else. But I don't know about time to show you something else, so we'll see. Let me do binary codes. So there's only a couple here that I want you to actually remember. So we have these codes. So we have BCD, which is important. That stands for binary coded decimal. This one is important because when you want to transmit information back and forth, if it's what we call mission critical information, you need some kind of what we call error minimizing code, and that's what gray code is. This is important because remember we said that numbers are represented, or anything that's represented in a digital device is going to be represented as zeros and ones. So numbers are kind of easy to think about. Codes are easy to think about because they're just groups of zeros and ones, may or may not have position weighting. But what about letters of the alphabet or characters on the keyboard? Well, that's what this other type of code is. You might have heard of Ascii code. So this is a way to represent other symbols like alphanumeric letters, alpha letters in a digital device. So we'll talk about the Bcd system. We'll probably run out of time, and I'll probably have to come back to this. Okay, so BCD, that stands for binary coded decimal, and it's really easy to go from BCD to binary. It's one advantage to BCD. The big thing though is this right here. This is the one you want to mark. So an LED makes use of the BCD code. So there's something called a thumb wheel with the PLC and the LEDs. You can drive these. Now let me go and show you what a LED is. Actually, maybe, yeah, I'll go ahead and show you now. I'll probably run out of time, but let me just show you, and we'll probably pick up with this next time. You've seen these before. You've seen these. These are the lights. Look at this. These are those digital lights you might have on your, well, there's actually two types of these. There's the LED light emitting diode, and there's the LCD, which is probably what you have on your cell phone. LCD is liquid crystal display. The technology is different, but the thinking is pretty much the same. Basically, you have these elements, these little lights. We'll call them lights, but they're really called diodes. They're rectangular diodes, and there's 7 of them, and they're all labeled A through F. And what it is if you think about the way this drawing is, depending on which of these switches you close over here, you can light up certain diodes. So if I do this, if I have it like this, if I light up this LED and this LED and this LED, that's a number 7. If I light them all up, then that's an 8. So with this 7-7 display, I can actually display the digits 0 through 9. And I think I made a picture for you. Look at this picture. If you go down on this picture and zoom in on it, you can see in that, oh, I don't know, okay. You can see in the middle here, where depending on which switch you close over here, you can actually display the digits, they show 1 through 9, but 0 through 9. And the way you do that is by using, right here, over here, we'll put in the number in BCD, and this thing right here is that. It's a BCD, the 7-segment display driver or decoder. And so depending on what number I put in over here, it's gonna light up over there 0 through 9. So that's kind of where we're going with this, but people are starting to sign off and I'm out of time. So I think this is probably a good place to stop, and I'll pick up with this next class. And guys, I don't know. I got an email from somebody in the office, and they said that the deans were considering my request, and I don't know. I don't know. I'm gonna see if I can get a hold of somebody and see what's going on with my request, and just keep a eye on your announcements in case we got to just kind of at last minute. I say, hey, we're gonna meet face to face and be ready. If we do though, I know you guys wear your mask, but you got to have a mask with you and make sure you wear it properly, not just have a mask. The thing is, when I'm on campus, I see students, everybody has a mask on, but when I drive up Calhoun and look at those bars, and I see the same students in there, I don't know if it's the same student, nobody has a mask on. That's the part I'm afraid of. So if we do end up going face to face, or whenever that happens, at some point, you got to make sure you wear your mask the right way. Nose and mouth covered. Well, I got a class coming up, so guys, you guys sign off here. Thank you for hanging in there, and have a great rest of the day. I'll stick around just for a minute in case anybody has a question, but then I got to run. And then there was one student that had a question about the quiz. Let's save that into next class, and we'll talk about it since my quiz is still open. Anybody have any other questions or comments? Okay, going once, going twice. All right, guys, have a great day, and I will see you.